So, what is work done by a force? So, work done by a force is defined in the following way. It is a product of the force and the displacement of point of application of the force and along the direction of the force. Let us take an example. Say on the ground there's a bag and a suitcase, and a person is dragging a suitcase. There is a person walking along and dragging the suitcase with him. And after a certain time, the same person has moved a certain distance, as you can see. So the point of application of force is this P. So displacement of point of application of force, as you can see, displacement is along the ground. So there it is, the displacement S of point of application of force S. And let's look at the force. And the force applied by the person is in this direction F. And throughout the path it's same. Suppose we are talking about a constant force. So this is the force F here. So even when the bag was here during an intermediate stage, there was a bag, and there also you would have had the same force F. Okay. So displacement of the point of application of force P is S, and the force applied is F. So we can say that this force is F, force is F, and displacement is S. And suppose the angle between the force and the displacement vectors is theta, then as per definition, what is work done is the product of the force and the displacement of the point of application of force and along the direction of the force. That means you have to calculate the force and that displacement, the component of the displacement in the direction of the force. So we'll make a diagram. So this is the diagram. So that as per definition is the product of the force and the displacement in the direction of the force. Displacement along the direction of force means you have to calculate the component of the displacement along the direction of the force. So the displacement vector, let's make it component along the direction of the force. So in the direction of the force, we'll draw up a perpendicular, and the component, the required component is S cosine of theta, where theta is the angle between the force and the displacement vector. So work done, W, work done by the force by force F in displacing point P by S is given by F times S cos theta. Now you can these are actually vectors, force and displacement. So force vector and displacement vector. So we can also write work done as F dot S. This is the work done for a constant force. If the force is not constant, then how to calculate work done? So work done by a variable force. Say during a point P is being displaced in the following way, this following path, and you may draw a coordinate system, this x, y, and z. Okay, and see, this is the direction of the path as shown by this green arrow, and the point P is being displaced from say point 1, position 1 to position 2. So let us take at some point of the path, the point P is here, and displacement is this way actually, that's tangent. So a small displacement is given by dr, the rate of change, the change in the position vector, right? A small dr is a small displacement. It's got to be dr actually, because displacement along, so dx is the displacement along x-axis. That means dx is a change in the x coordinate, right? Dx is a change in the x coordinate of particle during its displacement. And similarly, dy is the displacement along the y-axis, and dz is the displacement along the z-axis. So the total displacement dr is obviously the vector sum. So dx times I cap plus dy times j cap plus dz times k cap. So that is actually the change in the d of this. D means a small change. So dr as this r is x I cap plus y j cap plus z k cap. So however, so in during this small displacement dr, suppose the force is F. Okay, so we are going to write here on top here. So during displacement at dr, what is the work done? Dr work done by the force is F dot dr. Now the during its journey, so from 1 to 2, position 1 to position 2, what is the total the work done by the force? You have to add means integrate. So integrate from position 1 to position 2 F dot dr. That means during these small displacements dr is and maybe the force changes, and again small displacement, maybe the force changes like this, and again a small displacement, maybe the force changes like this. So you have to add up all these small, I mean what you do, you break up the path into infinitesimally small displacements like this dr each, and calculate the work done during this small displacement, and then you add them up. So that is the meaning of definite integration. Now let's learn about no work forces. No work force is so if the force is perpendicular to the displacement, then it is known as no work force. For example, I'll say that suppose a person holds a bag on his head and walks down a certain distance. So final position of this same person walking with the bag in his head, there it is. Okay, so the displacement of the bag is this way, s. Now if you say that, okay, what is the work done by gravity? Now here see, so gravity means weight of the bag is mg acting downwards, mg acting downwards during the whole path. Say any intermediate position of the bag, it acts downwards. So here for this displacement, so for displacement of the bag, the gravity force acting on it is a no work force. See, that doesn't mean that, I mean, all forces are no work force. The person will apply some force. See, the force between the head of and the person will apply some normal reaction and also a forward force to push it along. So this is actually the friction. So that is doing work obviously, but with regard to this gravity, this force, this mg, that is a no work force for this particular displacement. So in this problem, the box, so this is the box actually, the box displaces by 10 meter as shown in the figure. So find the work done by the forces. Find the work done by forces F1 and F2 during this displacement. So as you see the displacement vector, here I will draw displacement vector S. So the work done by F1, work done by force F1 is how much? So if as these are all constant forces, so F1 dot S, that means F1 is 100 Newton multiplied by 10 multiplied by cosine of 60 degree angle between this. So this makes it 100 into 5, that is 500 joule. And while for the same case, work done by F2 is, so F2 dot S, so is 30 Newton multiplied by displacement 10 multiplied by cosine of the angle between this. So that displacement vector is in forward direction. So angle between the displacement vector and the force is 180 degree. So it's cosine of 180 degree. Cosine 180 degree is minus 1. So that is minus 300 joule. So, problem number 2, find the work done by the force 3I cap plus j cap minus k cap in displacing the particle from the following coordinates. So here this is also a constant force. So simply we can apply work done is equal to F dot S. No, I mean, integration as such. So the position was 1 to 1 and final position is 5 3 4. So position vector at start was this r1, and position vector finally is r2. So displacement vector is the change in the position vector. As you know from triangle law, r1 plus displacement is equal to r2. So therefore s equal to r2 minus r1. So therefore s is equal to r2 means 5 I cap plus 3j cap plus 4k cap minus I cap plus 2j cap plus k cap. So what is the displacement vector? You just subtract the x, y and z coordinates. So 4 I cap plus j cap plus 3k cap, this meter, right? Now with the work done by the force, simply apply the formula of dot product F dot S. So this F has components, the x component 3, that will be multiplied by the x component of displacement plus the x component of force 1, y component 1 multiplied by y component of displacement 1 plus the z component of force minus 1 multiplied by z component of displacement 3. So work done will be this much joule. So let's calculate that. 12 plus 1 minus 3 joule, that is how much? 10. So the work done is 10 joule. This problem will deal with a variable force. Here there is a block, and the applied force on the block is equal to kx as shown in the figure. Applied force on block is F equal to kx, where say x equal to 0 is the initial position of the block as shown in the figure. So initial position of the block, and the x-axis is chosen. X-axis is chosen as in figure. So find the work done by the applied force during displacement of the block by A. So the displacement will be A. So here what we do, this is a variable force. So at any intermediate position, let x be the x coordinate of the block, and then a small displacement will be dx, and the force is obviously F equal to kx here. So during displacement dx, so during displacement dx, what is the work done? So it's actually kx dx. So the total work done during the path, you have to integrate. So integral kx, or we can directly apply the formula. We have already proved a formula, that fx dx or f dot dr, right? Integral f dot dr. Okay, so that is fx force multiplied by dx. So the limits of x will be from 0 to a. So that is k, this is x square by 2. Put the limits. So it is half k a square. Okay, so work done by a variable force from in displacing the point P from position 1 to position 2. So at a certain point, particle P is acted upon by a force F, and a small displacement dr happens. So we have proved this already in a previous page. So it is integration of F dot dr from position 1 to position 2. Now let's see how it looks like if the forces are given in terms of the x, y and z component. Now here the force will be F given in terms of x, fx I cap plus fy j cap plus fz k cap. This may be constant or may be variable also. So for the general case we have to take it variable forces. So dr is dx I cap plus dy j cap plus dz k cap. So the work done here, so if you do dot product f dot dr, so it's fx dx plus fy dy plus fz dz. This is the integration. So it's integration of fx dx. The coordinates will be from x1 to x2 plus fy dy from y1 to y2 plus fz dz from z1 to z2. And obviously the functions, how this fx, fy and fz vary with the coordinates, that functions will be given in the particular situation. In example 4, let us try out to find work done by the force 2x I cap plus yj cap plus zk cap in displacing a particle from 0, 0, 0 to 2, 1, 4. So here in this problem we will apply the formula directly. W is integral fx dx plus integral fy dy plus integral fz dz. So integral fx, so fx equal to 2x times dx plus fy is y times dy, fz is z times dz. So now we will put the limits. So x varies from 0 to 2 and y varies from 0 to 1 and z varies from 0 to 4, and thus you can find out the values. So this will be 2 by 2 into 2 square minus 0 square plus half was, so 1 square minus 0 square plus this again half 4 square minus 0 square. So this is how you can calculate work done. We have to find work done by the force y I cap plus x j cap in displacing a particle from 0, 0 to x naught y naught. This is also variable force, as you can see, and we will apply the formula of work done. Integral fx dx plus integral fy dy. So as you see, fx equal to y, so integral y dx plus integral x dy. Now it may seem that it's impossible to integrate, but it's not like so. See, x y, a change in x y means d of x y. What you can write? It's x dy plus y dx. So this work done you can write as is from this term. So integration of y dx, so you can write it together, integral of y dx plus x dy. So that is nothing but integral of d of xy. Okay, so integral of d of xy is actually xy, and the limits will be 0 multiplied by 0 to x naught multiplied by y naught. Final values of x into y is x naught multiplied by y naught. So x naught y naught minus 0 into 0. So that is x naught y naught. That is the answer. Work done. See, in this case there is a bent rod, as you can see on this figure. This whole thing is a bent rod, and a ring of mass m is sliding down the bent rod. It is released from the position shown above at a height h from ground. Find the work done by gravity force on the ring during its displacement. That is, while the ring is released at the topmost point at a height h until it reaches ground, you have to find out the work done. So the final position of the ring will be there. And during its journey at any intermediate position, let's draw the ring here. And what is the gravity force acting on the ring? During its journey, during all points, the gravity force is mg, the weight of the ring. Ring starting point, any intermediate, all the intermediate points, the force is equal to mg. And as per definition, what is the work done by the force? This is a constant force also. Product of the force multiplied by the displacement in the direction of the force. So displacement, the component of the displacement in the direction of the force is s downward, and this s is equal to h, as you can see. So the work done, required work done by gravity, is mg multiplied by h. Now this problem is to show that work done is dependent on the frame of reference. So three frames of reference are here: observer A, observer B, and observer C. See, observer A is standing on ground, B is starting to move with a constant acceleration 2 meter per second square towards the right, and C moves with a constant velocity of 5 meter per second towards the right. Now the cart begins to move obviously from rest with a constant acceleration of 4 meter per second square. Find work done by friction acting on the block from t equal to 0 to t equal to 10 seconds. So as observed by A, B and C. Now friction on the block acts in the forward direction, as you know, and as there is no slipping, so friction on the block we can write like this: F is equal to m into A. So acceleration of the block is given as 4. So 5 multiplied by 4, that is 20 Newton. So that means friction acting on the block is 20 Newton. Okay, and displacement of the block. So in 10 seconds, right? In 10 seconds, displacement of block is starts from rest. So half acceleration times t square. So that is 200 meter. So first part of the question is to find out work as observed by A. So with respect to A, the displacement is equal to 200 meter, as A is ground frame and the force friction acting on it is 20 Newton. So therefore work done is equal to 20 multiplied by 200, that is 4000 joule. So in the second case, displacement of B is 100 meter towards the right. So with respect to B, displacement of the block is 200 minus 100 meters, that is 100 meter to the right. And see, displacement is frame dependent, but force isn't frame dependent. So work done, therefore work done by friction, W is equal to, what was the force? F multiplied by 100. So if it's 20 multiplied by 100, that is 2000 Newton. So displacement of C is 50 meter. So with respect to C again, displacement of block is 150 meter to the right. So therefore the work done by friction is F multiplied by 150, that is 20 multiplied by 150, that is 3000 Newton. Now suppose if there is an observer D, so who is having acceleration, say, and so what would be the work done? What would be work done by friction on the block relative to D? Now say D is having acceleration of say 8 meter per second square to the right. I mean from 0 to 10 seconds, right? Sorry, in all these cases I have mentioned work done as Newton, but the work done has unit joules. So it was slip of a tongue and slip of a pen as well. So work done will be joules. So whatever I said 4000 Newton, no, it's 4000 joules. Thank you. So in these last videos I have mentioned work done as 4000 Newton, 2000 Newton. No, it should be joules. I'm sorry. So that means in this problem we have one more observer. His name is D, and D is running with an acceleration of 8 meter per second square, and there is a block, and the block is having block starts with an acceleration of 4 meter per second square. So find work done by friction on the block. But there is a card beneath it, okay. The friction we have found out, it's 20 Newton. So in 10 seconds, displacement of the block, as you know, that's 200 meter to the right, and in 10 seconds displacement of D is equal to 400 meter, right? So that is half 8 multiplied by 10 square. So this will make it 400 meter towards the right. So as observed by D, as D observes, the block is displacing in the following way. The block is moving towards the left and having a displacement of 200 meter. Okay. So as observed by D, the block has a displacement of 200 meter to the left, and friction acting on it, friction acting on block is, that is as usual, 20 Newton to the right. So therefore work done by friction you can calculate. Therefore W, that means work done by friction from this 0 to 10 second is force of friction 20 Newton multiplied by 200 meter, but you have to put here cos 180 degree because friction is in the forward direction and displacement is, friction is towards the right and displacement is towards the left. So this makes this minus 4000 Newton.